Hi everyone. This is Pre-Calculus 12. Again, we're going through the second half of section 3.1 on polynomials. And we're going to start off with a few basic points. Again, you should have these notes in your Microsoft Teams class notebook section. If you have any troubles with that, let me know, but you can either print them off ahead of time or use them to follow along as we're going through this. So just a few reminders. It says real zeros of polynomial functions. That is the point, meaning the real zeros is the point where the graph crosses the x-axis. Another name for that is zeros, x-intercepts, and roots all mean the same thing. I just want to add on to here that if it crosses the x-axis, we did this in the last video, that's also the point where y is equal to 0. And if f of x has a factor of x minus a, then x equals a is a 0 or root or x-intercept of f of x. This is going to make more sense when we do actual examples with numbers, but this is a good way to start things off. You can come back to this maybe after you do the examples. X equals a is a solution of f of x equals 0, and the point a0 is an x-intercept of f of x. So if we have some polynomial f of x, then all of these things are factors or points to note about that polynomial f of x. Okay, so I feel like sometimes with all this wordiness and these definitions and all of that, it's difficult to get clarity on what it is that I'm talking about. So let's start with our first example, which says find the real zeros of f of x equals negative 3x to the 4 plus 3x squared. I will just stop for a second to highlight this and say, when we're talking about the real zeros, I could call those the x-intercepts, I could call that the solution, I could call that roots. So know that I'll use those words interchangeably. You'll see them in questions, but that's what they're all talking about. So the first step in being able to do that is I'm going to refer back to all this stuff I talked about. I want to try to make my equation look like that. So I want to factor it out and break it down to be able to pick out the things that I need from this. So a strategy or a method for doing that is factoring. That's what we learned how to do for the last few years, actually. And we've gone through different types of factoring, but when we look at this is a binomial, so there's 2 terms. The easiest way to factor it out is we look for the greatest common factor by looking at it. So when we look at this, we can see that clearly they both have a 3 and an x squared, but it's probably a good idea to get rid of that negative in the lead term, the lead coefficient. So I'm going to say that my greatest common factor is negative 3x squared. So I'm going to pull that or factor that out by dividing both terms by this. So when I divide out negative 3x to the 4 by negative 3x squared, it's going to leave me with x squared on the inside. And when I divide 3x squared divided by negative 3x squared, then that's going to leave me with a minus 1 on the inside. I'm not spending much time on the factoring part because I feel like by this point you all know how to factor. But I did, maybe I'll just, in brackets over here, I will just mention that the greatest common factor that we pulled out was the negative 3x squared, because basically what factoring is looking at the terms and trying to find similarities. What do these things have in common? And that's what we pull out. Okay, so negative 3x squared, but when we go to look at this, I'm going to use a different color to highlight this. I can actually factor that further. So notice that these are a difference of squares. X squared and 1 are both perfect squares, technically speaking. And so we know from past experience that that would factor to x plus 1 and x minus 1. So now I have, and maybe it's a good idea for me to write this out, f of x equals negative 3x squared times x plus 1 times x minus 1. So I have a fully factored polynomial. It's all of a sudden a lot easier for me to find the real zeros or the roots or the x-intercepts. Because I would do that by setting this whole thing, you know what, I know I'm changing my mind left, right, and center here, but let's set that whole thing equal to 0. That's how we find the solutions. So technically, to set the whole thing equal to 0, that means I can set them each equal to 0 separately. So 0 equals negative 3x squared, 0 equals x plus 1, and 0 equals x minus 1. Because if any one of these three parts, that, or that, is equal to 0, then the whole thing would be equal to 0. So that's technically what we're doing. I don't expect you to write every single little step down like I am here, but I want to make sure that it's clear to you in the video. So if we were to solve for x here, I would divide by negative 3. That would still just give me 0. And when I square root that, basically is just x equals 0. Here, I would move this plus 1 over, so I would subtract 1 on both sides. That would give me x equals minus 1. And same thing here, I would want to move this, or you could say move it, but actually we're adding 1 to both sides. So that would give me this. And so therefore, this is my little symbol for therefore. You're going to see it all year long, so get used to that. The zeros, or the x-intercepts or the roots, whatever you want to call them, are x equals 0 and plus or minus 1. So that's actually what our solution is after going through all of this. So I know that we've added in a few new steps, but a lot of this, like the factoring, breaking this down, solving for 0, like setting it equal to 0 and then solving it, those are all things that you've done for the last several years. The new part is, I guess, the vocabulary or the terminology, or putting this all together to see that that's the reason why you learned factoring and algebra and all this stuff over the last few years. Okay, let's do another one. So we also want to find the zeros or the roots of this, and we want to take a similar approach by factoring this. But notice how this time we have 1, 2, 3, 4 terms. And just by looking at it, we can tell they don't all have something in common. So I know that I'm going to have to use fancier factoring than just the basic greatest common factor style. So when I have 4 terms, we learn something called factor by grouping. So I am going to try this. It doesn't always work, but I'm going to try it out to see if it might work. And that is to group the first 2 terms together and group the last 2 terms together, and or you're always welcome to rearrange them as well. So I could have moved the x's together and moved this minus 2 over by the other 2. Any which way that I move it around, I'm looking for similarities only between the terms that I've grouped together. So I can look at these 2 and just pretend the last half doesn't exist for a minute. And if I just zoom in on these 2, I notice that they both have an x squared in common. So if I divide out an x squared, then here it's going to leave me with just an x, and here it's going to leave me with minus 2. And then if you take a look at this part that I had split in half, notice that I'm going to leave that plus sign out there, and I'm going to put this in brackets to try to show you clearly what is going on. And although you don't need this, I'm going to put in these big, huge blue brackets to try to really make it clear to you. We're treating this like one big giant term, and this like one big giant term. And I'm looking to see, is there something that those 2 terms, because I've clumped them together, is there something that those 2 terms have in common? And that would be yes, this x minus 2. So I'm going to draw this really big exaggerated version of this. I'm going to pull out the x minus 2, and by saying pulling out, I'm technically dividing it out. And inside then, I would have left this x squared. And then if there's nothing there, and I've divided out the x minus 2, leaving a 1 there. So this looks ridiculous, and you don't actually need to draw it quite like this. Technically, that's how we got our x minus 2 and then the x squared plus 1. And then we set this equal to 0 just like we did in the last one. This is this time not a difference of squares. It looks like it almost is, but there's a plus sign in between. So I am again going to set them equal to 0 separately. But this one's a little more complicated. Here I would add 2 to both sides, and this would be x equals 2. So there's one solution. And here, I would actually have to move this over and it would become a negative 1 equals x squared. So technically I'd have to square root them both. But x equals the square root of negative 1, well, that's not a thing. Like, that's an imaginary number. So our solution after all of that would just be x equals 2. We would have to reject the other one because it's not a real number, our answer. It ends up giving us an imaginary number, which is not a solution. So I purposely have chosen, like the first one was pretty straightforward, we can go through it, but the second one is a little bit unusual in that one of the solutions was an imaginary number. So I thought it would be helpful to go through an unusual one together so you can see the different forms that this may take on. Okay. Keep in mind, you can pause at any point if I'm going too fast or you're not quite sure. That's the beauty of having these videos, is you can go at your own pace. So you can hit pause. I would suggest that you go back and try some of those on your own because it's a different thing when I'm going through it for you. So go at your own pace. Pause, rewind, do whatever you need to. Okay. Moving on to zeros of a polynomial function of degree n. So, an even degree is an nth degree intersects the x-axis 0 to n times. Okay, so I get this. You probably don't really get what this is saying. So let me show you with an example. We already looked at some even degree polynomials in the last video where we looked at n behavior, so I'll refer back to that. But if we, for example, have a graph, because I think showing you on a graph is going to help you to understand this, it's saying that like nth degree, so for example, if I made this, like if we're talking even degree, let's say we had a 4th degree polynomial, then how that would look if we had a 4th degree, if it intersects 0 times, maybe it goes like this and it's been moved up or translated up so that it doesn't even intersect the x-axis at all. So that would be an example of 0 times. Okay, let me show you an example of what the maximum number of times would be. Like if I'm talking 4th degree, then instead, let's say I slid that down, it could go like this, and it would intersect 1, 2, 3, 4 times. So this is showing you the minimum number of times that it intersects, which would be 0. And this is showing you the maximum number of times if it's like, for example, if I'm using a 4th degree polynomial. It could be a 6th degree, in which case I could go like 1, 2, 3, 4, 5, 6. So you get the idea of what we're talking about. And I just want to quickly show you before I switch over that you could even have something weird like this where it goes 1, 2, and then up like that. So it's actually only intersecting 2 times. So there's a lot of unusual ways that this could show up. But that's some of the forms that it could take. If we have an odd degree, then it intersects the x-axis a minimum of 1 time. So notice in the last one it was 0, up to n times. So if we're talking cubic, then it would be 1 to 3 times. If I'm talking to the power of 5, x to the power of 5, then it would be 1 to 5 times. And the reason for that, let's take a look at this, is if I have just 1 time, then it could take on a form kind of like this, where it's only crossing there once. But if I have instead 3 times, like a cubic, it could go like this, where it's crossing 1, 2, 3 different times. Because their end behavior shows that they start and end in different directions, that's how we know it's got to cross at least one time. Whereas with the even degree ones, like up here, it's possible for it not to cross at all because they start and finish pointing in the same direction. And notice for all of these graphs that I've drawn, I could have flipped them over the x-axis to show the opposite, but this rule would still be true. I'll show you a quick example. If instead I started up here because it was flipped around, oh man, that was not good. But let's say it goes like this. So we'd have 1, 2, 3 different solutions just like in this one, but they're going in the opposite direction. So that is helping to clarify what's going on with that. And then let's look at turning points of a polynomial of degree n. If a polynomial has n turning points, it has a minimum degree of n plus 1. Okay, so I'm going to show you, again, I think using graphs is the easiest way to talk about this. So let's say I have a funny looking graph like this. 1, 2, 3, 4, 5. Okay, if a polynomial has n turning points, I'm going to underline it in blue and we're going to look for what those are. Like where it changes direction is a turning point. So see how here it's going up and then it starts going down? That's my first turning point. That's my second one, my third, and my fourth. So this has 4 turning points. That shows you what I'm talking about. So that means it must have a minimum degree of 5 because it's n plus 1. Okay, that is, I believe, how the book does it, but I also have a different method that I actually find easier, so I don't need to worry about this n plus 1 stuff. Another way that you could go through this is what I call changes in direction. So what I would do is I would start down here and go 1, 2, 3, 4, 5. So what I mean is like up, down, up, down, up. So that would be 5 changes in direction. So kind of like with everything else, what I'm going to say to you is I want you to pick the one that makes the most sense to you. So if you feel that this green 5 changes in direction really works for you and that's how you want to do it, go for it. If this 4 turning points, like counting the corners or the turning points helps, go with that. Use both. It doesn't matter. Just make sure that you figure out which one helps you to know how to do this. So that's what we're talking about. And then the next thing is multiplicity of a polynomial. When one solution is repeated more than once. So in this equation, we have y equals x plus 3. If there's nothing there, it means to the power of 1. And then we have x minus 2 cubed. So this, because there's a cube there, I guess I should point the arrow to the actual exponent. This means we have a multiplicity of 3. And that means something on a graph, but let's just draw your attention to that part for now. So that means at x equals 2, because it's always the opposite of what we see here, it means that the solution is repeated or there's a multiplicity of 3 at that point on your graph at x equals 2. Okay, so what do we do with this? Well, let's take a look at an example and figure it out. Find the zeros and the multiplicity of the following polynomials. First things first, this is not factored and we want it to be factored, so that's the first thing we're going to do. First type of factoring we ever learned is looking for similarities. So take a look at this and look for similarities. X squared, they all have. So I can pull that out and that leaves me with x squared plus x minus 6. Okay, so we have x squared out here. And then I'm looking at this x squared plus x minus 6, and this is, I can tell it's a trinomial. We've done lots of factoring trinomials. I'm looking for two numbers that multiply to negative 6 but add to 1. So I know that it's got to be positive 3. Whoops, what's going on here? And x minus 2, because, and I can just double check, this times this does give me negative 6, and 3 plus minus 2 does give me plus 1, so I know that I've chosen the correct ones. So it asked for the zeros. Oh, first of all, I guess I should set this equal to 0, and I don't need to write this all. I've been writing it all out for you, but I think by now you know how to do this. We could set them all equal to 0 separately, but by doing that, what we would find is our solution from this part would be 0, from here it would be negative 3, and from here it would be positive 2. So to give my answer and to give it properly, I'm going to say my zeros are at 0 with a multiplicity of 2 because it was x squared here. So because of this x squared, I know it has a multiplicity of 2. My other 0 would be at negative 3 with a multiplicity of 1. But I mean, that's sort of not needed or not required, but I just wanted to make sure that you get clearly that you understand like what this is talking about. So a multiplicity of 1, like we don't need to say that. That's the assumption, is that they all have a multiplicity of 1. You only need to state the multiplicity if it's more than 1. So then I don't know, I just wrote it, but you don't have to write it. Okay, this would be a good time for you to pause and try part B on your own, since we've gone through the other part together. But I'm going to keep going, and you can control that on your own video. But notice how this all goes. This has the potential to look like it's tough. No, it's the same thing as what we've been doing. It's just gotten a little bit longer as we go through this, right? So basic factoring isn't going to work, because if we look at this, well, first of all, there's 1, 2, 3, 4, 5, 6 different terms. Just because more things have been added to it, it doesn't mean that the level of difficulty has gone up. Just get into the habit of applying the same steps. Keep in mind that you're doing the same thing, but we've just added in another step or two. So basic factoring is not going to work. We can look to start factor by grouping. So we could try to put them into pairs and see, like, is that going to help us or is that going to work? I am conscious or aware of the fact that the last two really don't have anything that we're able to do with them. So I'm just hoping, and this often does end up magically working out, so that x plus 1 ends up being a factor in the other two groupings that we've done. So let's give it a try and let's see what happens. If I just ignore all of this and just zoom in on the first two, I notice that they both have an x to the 4. And when I take that out, I'm left with x plus 1. Look at that. It does look just like the one at the end. So hopefully that happens with the next one. When I look to see these two, I can factor out negative 2x squared. And look at that. What's left inside is, in fact, x plus 1. When I divide out this by negative 2x squared and this by negative 2x squared. Next door. Just next door. Yeah. Sorry. And here we would have plus and then x plus 1. So when we take a look at, well, you don't actually have to do this, but I like to do it to really try to make it obvious. We want to treat this like one big term. We want to treat this like another big term, and we want to treat this like another big term. So that's ultimately what we're trying to do. So step back and look at the big picture, look at those big blue brackets, and think to yourself, maybe I'm going to do this, but shrink them down a bit. What do all three of these terms, and I know I'm calling them big terms because they've got a lot going on, they all have an x plus 1, so I can pull out an x plus 1. And by pulling it out, what I mean is I divide this by x plus 1 to leave a 1 there, divide this by x plus 1, divide this by x plus 1. And then I look to see what does that leave me with inside. And maybe to make this clear, because there's so much going on, I'm going to circle them in green. If there's nothing there, it's just a plus 1. So I have x to the 4 minus 2x squared plus 1 left inside. Okay, so again, my brackets are way too big, and this looks a little bit ridiculous, but I am going to carry on. So I have x plus 1, and then we can actually factor this out. So it's a trinomial again. When I look at it, I'm looking for two numbers that multiply to 1, and they add to -2. So if I'm looking for two numbers that multiply to +1 and add to -2, well, at the start here, because I'm starting with x4, I know it must be x squared. So I'm going to do this and set up my two brackets. They both have an x squared at the start. What multiplies to +1 and adds to -2? Well, it must be -1 and -1. Okay, so yeah, this is a little bit longer than the last one, but it's still the same thing that we're doing. So I'm going to zoom in to show you. We can still keep going because notice what we have. We have an x plus 1. I'm going to do this in color so you can see which is which. We can factor that, that's a difference of squares, to make it x plus 1, x minus 1. And we're going to do the same thing over here. That factors to x plus 1, x minus 1, because they were both a difference of squares. Okay, so this is not the level of difficulty, but this requires extreme organization because you've got to keep things straight here and figure out what's going on. Let's do that. There's an x plus 1, there's another x plus 1, there's another x plus 1. There's an x minus 1, and there's an x minus 1. So in order for me to appropriately put this together, I'm first going to simplify this. I'm going to take all the pink underlined ones and say, okay, actually I'm going to start with the blue ones first because there's less. X minus 1 squared, and I have x plus 1, and there's 1, 2, 3 of them. And just a quick tip or a hint, because I have so many things to keep track of, I highly suggest the different colors or the underlining or the squiggly lines, whatever. All of these are organizational things that I do to keep track of things, because in all these years of teaching, what I have noticed is that a lot of students know how to do the math, but they just forget they left off an x plus 1, or they forgot a negative here. So these things are a good way for you to keep organized to minimize mistakes. And it's just good habits to get into. So whether I'm marking your work or whether someone next year is marking your work, whoever it is, it's important that you set it up clearly so that it's easy to see the thought process and what you were doing and to get to the end result. Okay, so good way to check this out to see if you haven't left anything behind or you've kept things straight is look at the end result. We have 3 x's here and 2 x's here. So x to the 5 is what the original should have been. And so I go back to the original g of x and see it was in fact x plus 5. So that kind of makes sense. And then for my, what did it ask for, roots or zeros? What did it say? It said find the zeros, but it doesn't matter what we call it. I could call it roots or zeros, or I could call them x-intercepts. But let's say it appropriately. I would say that it's at +1 with a multiplicity of 2, and at -1 with a multiplicity of 3. So that's ultimately what we were looking for. Okay, so that is the second portion of 3.1. I hope that you found that helpful. This, again, is your suggested assignment. You decide. 4 to 5, I'm giving you all. I would suggest you do them all. When you get to number 9, odd letters, meaning A, Z, E, etc., etc. But if you're struggling with it and you need more practice, then just do them all.